In the last lecture, we looked at variation of emissivity of metals. And we saw that if we assume that the directional spectral absorptivity, which is equal to direct spectral emissivity, is assumed to vary as square root of the temperature and inversely proportional to wavelength, then we saw that the directional total emissivity varied linearly as the temperature, and the directional total absorptivity varied as root of Ts and Ti, where Ti is the source temperature. So, we clearly saw that the emissivity of metal depends only on its surface temperature, while the absorptivity depends both on the surface temperature and the source temperature. So, this distinction was brought out clearly. We also saw that if by chance Ts was equal to Ti, then alpha prime is equal to epsilon prime, as per Kirchhoff's law. But this is a special case. In general, we saw that the ratio of alpha prime to epsilon prime goes as root of Ti by Ts, clearly showing that in many cases, for example, if Ti is close to 6000 Kelvin, the sun's temperature, and Ts is 300 Kelvin, then alpha prime by epsilon prime is root of 20, which is around 4.5. So, in the case of metals, you see that the solar absorptivity is about 4 to 5 times larger than its infrared emissivity. So, this could be called as selective surface. A surface whose properties depends on the wavelength and which enables you to. So, if we draw it graphically, you can write alpha prime lambda equal to epsilon prime lambda, and it varies as 1 over square root of lambda. So, you can clearly see that in the wavelength below 1 micron, absorptivity is high, while at higher wavelength, let us say around 10 micron, emissivity is low. So, if such a material is put out in the sun with solar radiation impinging on it, it will reach a temperature higher than a surface whose properties do not vary with wavelength. Okay. And we saw just now that the absorptivity of metal is about 4 times higher in the solar region compared to the infrared region. So, that advantage it has, but you can improve this advantage further if you take a metal substrate and put a coating. You put a semiconductor coating For example, it can be copper oxide on copper, then this copper oxide will absorb strongly in the solar region, and then it will rapidly this region, and then it will come down rapidly in the infrared region. So, in the infrared region you will see the effect of the substrate. So, let me just read all this. This is how the metal behaved. The semiconductor coating gives you a higher absorptivity in the solar region, and then it merges with the so this additional absorptivity is given by the coating. So, coating typically a micron or less thick improves the absorptivity in the solar region, while keeping the emissivity in the infrared region unchanged. So, by that the ratio of alpha prime to epsilon prime can be as high as 10, twice that of pure metal. So, these selective coatings are used in solar collectors to achieve high temperatures, and we will show some examples little later in this lecture. Now, let us look at some other examples of materials and see how their emissivities vary with temperature. In this figure, you see that the emissivity of graphite varies roughly linearly with temperature, although it is not a metal, it is a non-metal. And you see tungsten, which is a metal, has a linear variation with emissivity. Polished gold has a roughly linear variation of emissivity with temperature, and so does magnesium, except Inconel shows somewhat nonlinear behavior in its variation of temperature, while oxide layers like the one you see here, magnesium oxide, the emissivity decreases with temperature. So, generally you see that for metals, majority of metals show an increase in emissivity with temperature. Now, in the next figure, you see the dependence of the directional spectral emissivity of the material, and the data is shown in the forms of these squares and circles, while the line here in blue or green is really shows the theoretical relation that we had assumed, which is proportional to square root of t and inversely proportional to square root of lambda. So, that behavior is the theory, so called Huygens-Rubin relation. And when the metal is oxidized, this is titanium, is oxidized, the emissivity increases, that you can see here, the effect of oxide layer. We will examine this issue a little further in today's lecture. So, you can see that although the data does not agree precisely with the simple theory, it does show a similar trend overall of a decrease in emissivity as the wavelength decreases. And so, this is the important reason why the emissivity of metals increases with temperature. Now, there are few more results here showing variation of spectral emissive wavelength. For example, you have molybdenum, you have iron, you have platinum, nickel, they all show a decrease in emissivity with wavelength, although the slope is somewhat different for different materials. But interestingly, copper does not show that effect. Copper seems to have an emissivity which does not vary that much with wavelength. Now, one probable reason why some metals do not show the predictions of simple theory is because there could be a thin oxide layer, because you see these are metals at high temperatures. So, unless you keep them in an inert atmosphere, an oxide layer forms on the metal, and the emissivity can be then controlled by the oxide layer and not the metal. So whenever you try to look for data from various sources, you have to be sure whether the metal whose emissivity is given is really a pure metal with no impurities, and whether it is really free of oxide layers. Because oxide layers have a huge impact on the emissivity of materials, and we will see that further in the subsequent slides. Now, here again we show the normal total emissivity, the total emissivity in the normal direction as a function of temperature in thousands of degrees Kelvin, and you see clearly that in the case of tungsten, the theory, and in the case of tungsten, the theory and experiment are not in very good agreement. Tungsten is the red line here, and the blue line shows the value of platinum, and you see clearly that platinum theory for platinum agrees quite well with the data for platinum, and the fact that in the case of platinum the theory and experiment agree, while in the case of tungsten they do not agree, could be on account of a small oxide layer on the tungsten surface, which is not there in the case of platinum. So, these issues must always be looked into when trying to use data of emissivity of metals, because oxide layers are usually there. They are not easy to avoid unless the metal is heated in an inert environment like argon. Otherwise, oxide layers will form, and one has to account for the oxide layer effects. Now, here we are showing you the variation of the spectral emissivity of tungsten as a function of wavelength. You see that beyond 1 micron, this decreasing effect of emissivity of wavelength is seen clearly. This follows the theory which we discussed, but at low wavelengths around the visible region, you see that emissivity is almost constant. This shows that the simple assumption we made that the epsilon prime lambda, the simple assumption we made that the emissivity is a function of wavelength and varies as 1 over squared wavelength is usually valid only beyond 1 micron. Below 1 micron, other effects come into play, and so the simple theory that we propose may not be valid. Now, here we show you the directional variation of emissivity at various wavelengths. This is pure titanium with a certain surface finish, and you see that in the visible wavelength here, the emissivity is shown as a function of the angle normal to the surface of the plate, and you see emissivity is almost constant from 0 degrees value of theta to almost 60, and then starts decreasing. So, this is a typical behavior of many materials, that emissivity remains roughly constant up to around 60 degrees, and then they start decreasing. And you see this tendency is seen at also 1 micron and 1.62, but beyond that at 4, 8 and 20 micron, you see that emissivity is continuously increasing up to about 75 degrees, and then it starts decreasing. So, the behavior of emissivity with respect to angle is wavelength dependent. At low wavelength, it has one behavior, and at high wavelength, it has a different behavior. So, when you are modeling the variation of emissivity of metals, this feature of metals, that the angular dependence of emissivity is a function of wavelength, must be accounted for, and you can see that variation is very different between low and high wavelengths. Now, here is an interesting example of the effect of coating on metals. Here what is shown is the reflectivity of white paint when it is coated on aluminum, and what you see is that white paint is a very good reflector in the visible. It has a value around 0.9 here. So, that is what we expect from white paint, to be nice and reflective in the visible. But when you go to the infrared beyond about 3 micron, you see that the emissivity, the reflectivity is very low. So, reflectivity is around 0.1, that means it absorbs 90% of the radiation. So, it is almost black in this region. So, this is the interesting factor. You look at a surface and it looks white to you in the visible, and hence you know it is a reflective surface. From there you cannot conclude anything about the behavior of the surface in the infrared. In the infrared, it is not a good reflector, it is a poor reflector. So, white paint is a selective surface whose behavior below 1 micron and above 1 micron are very different, and so this factor must be accounted for when you are trying to model the emissivity of white paint and aluminum. You have to account for the fact that the reflectivity of the material is very different, is around 0.9 in the visible and around 0.1 in the infrared. So, when white paint is coated on aluminum, it is still extremely good emitter in the infrared. So, that is why it is a very good paint to use to paint outdoor containers, which will contain, let us say, either petrol or other flammable material, and you want to keep the temperature low. So, you coat it with white paint. White paint is highly reflective in the region where solar radiation is impinging on the tank. So, it will not absorb much solar radiation. At the same time, whatever radiation it absorbs is able to emit very efficiently in the infrared, and hence it will keep the tank temperature sufficiently low, so that it can be safe for storage. So, this is a good example where a selective coating like white paint keeps the temperature of a surface low. But the example I quoted a little earlier was where we coat copper oxide on copper, which makes the surface a very strong absorber in the visible and a very poor emitter in the infrared. So, in that case, the selective coating of copper oxide on copper actually enables it to reach very high temperatures. So, one kind of selective coating, that is semiconductor on metals, that copper oxide on copper, helps you to get high temperature when subject to solar radiation. But if you coat a metal with white paint, it enables you to keep the surface at a low temperature. So, we are able to achieve both by a suitable selective coating. A black selective coating like copper oxide on copper, or a cool coating like white paint on aluminum. So, this is a way temperatures are controlled in satellite or in solar energy applications or other situations in engineering where you want to control this surface temperature through radiation. Now, here is an example of effect of surface finish on the directional variation of emissivity. Here you see an example of 3 different conditions: ground surface, honed and lapped. So, as you go from ground to honed to lapped, the surface getting smoother and smoother. The roughness height is going down from around 0.4 micron to 0.05 micron. So, smoother the surface, of course, higher the reflectivity and hence lower the emissivity. So, you see lower emissivity for our lapped surface and higher emissivity for a ground surface, but in spite of the honing and grinding or lapping, the angular variation of emissivity has not changed much. It remains almost similar. So, the state of the surface has not altered its angular dependence. It has altered the value of emissivity, but not its dependence on angle. So, for at least this pure titanium, you can have a single function which will account for the angular variation of emissivity with theta, without worrying about the type of surface finish that object has. And you must notice here that these measurements are made for a wavelength of 2 micron. So, the reason why this grinding, honing or lapping has not had a large impact on the functional variation here is because the wavelength of the radiation we are dealing with is larger than the roughness height that is depicted here. Now, this figure now shows how the hemispherical total emissivity, that is after integration over both angle and wavelength, varies with temperature. For copper, if you have pure copper, polished copper with no oxide layer, then the emissivity is very low, around 0.05. But this situation will not prevail for a long time in the real world. Very soon an oxide layer will form, even a thin oxide layer, and you see the emissivity suddenly jumps from around 0.05 to around 0.55. So, emissivity goes up 11 times on account of an oxide layer, and if the oxide layer increase thickness, it can go to around 0.8, and you make a really thick oxide layer, you can even get a black oxide. This is the standard coating used on solar collectors to increase the temperature of the collector. And so, you can see that oxide layer plays a very important role, can change the emissivity from 0.05 to 0.9. So, oxide layer should always be accounted for in while estimating the emissivity of metals. Now, this is depicted in a somewhat different way in this figure, which shows variation of the hemispherical total emissivity as a function of coating thickness for aluminum. And you can see that initially the emissivity increased rapidly from 0.05 to around 0.5 when the oxide coating is about 2 micron. Beyond 2 micron, it increases, but somewhat slowly, goes from around 0.5 to around 0.8. So, this gives a rough idea as to the impact of the thickness of the oxide layer on the emissivity of metals. So, it is important to have some information about the oxide layer thickness before you assume the emissivity of metals, because in engineering practice, pure metals with no oxide are very rare. So, you should be looking out for a certain amount of oxide layer thickness, which has a substantial impact on the emissivity of the metal. Now, this is an illustration of impact of surface finish and oxide layer on inconel X. For example, you see that newly polished inconel X has an emissivity close to 0.2, but if it is not polished, it is just received a clean, it is more like 0.3 to 0.4, but once the oxide layer forms on it, it jumps to around 0.75. So, here again you see the important role played by the oxide layer here, and important role plays by polishing the material after it is received. So, after received, you polish it, its emissivity goes down, but after some time an oxide layer forms, the emissivity jumps back to 0.8. So, this again is an important issue in making estimate of emissivity of metals. Now, we go back to our discussion on selective surfaces. A selective surface is one whose absorptivity or emissivity is a strong function of wavelength. Now, here is a picture of the observed normal spectral absorptivity of silicon oxide, a semiconductor, on aluminum, and you can see that it falls from around 0.9 in the region below 1 micron rapidly to around less than 0.1 beyond 2 micron. So, this is the kind of material we will need for solar collectors to absorb the sun's radiation strongly, and at the same time not to emit the radiation that is coming in the infrared from the surface. Now, real surfaces of course have complex behavior. For modeling perspective, you can replace this by a surface with absorptivity of 0.9 or 0.95 in the region below 1.5 micron, and assume it to be rapidly changing to an emissivity around 0.05 beyond 1.5 micron. This is simplification you can make. Or you want to be little more realistic, you can make an ideal approximation. You can assume 1 in the solar region and then rapidly transitioning to almost 0 in the region beyond 1.1 micron. So, these kind of approximations are made to calculate, and we will take up one example in this lecture. Now, here is a realistic depiction of the incoming solar radiation, which is around 1000 watts per square meter, and you can see it peaks around 0.5 to 0.6 micron. In the same figure, we have shown you the emissions of a black body at 100 degrees centigrade, 300 degrees centigrade and 400 degrees centigrade. And what you find is that up to 400 degrees centigrade, most of the emission from the surface is confined to the region where the reflectivity of the material is quite high, or alternately emissivity is very low. So, up to 400 degrees centigrade, the fact that emissivity is low in this region is advantageous in not losing heat. At the same time, when the same material in the solar wavelength region, that is around 0.5 to around 1.1 micron, you see that the reflectivity is very, very low. So, it is absorbing strongly here, and it has a very low emission here because of high reflectivity. So, this is molybdenum aluminum oxide selective absorber, and you can see that it is very useful to get a flat surface to reach temperatures of the order of 400 degrees centigrade without losing too much radiation in a region where the solar radiation exists. So, this kind of coatings are now being routinely used in solar collectors all over the world, and the basic principle here is, of course, is to have this coating thin enough not to unduly alter the emissivity of the material, which is already quite low, and at the same time ensure that you absorb all the radiation that is coming from the sun. Now, one more example we will discuss in this lecture or the next lecture is the temperature variation from a tungsten filament lamp, and you can see that a 60 watt bulb, 100 watt bulb, 150 watt bulb, as you go to higher and higher wattage of the bulb, the temperature of the filament is increasing slightly, from 2800 Kelvin to 2900 degrees Kelvin. And if you plot the black body emissive power at those temperatures, you can see that the tungsten filament lamp peaks at a wavelength of around 1 micron. So, the tungsten filament lamp is not peaking in the visible. So, tungsten filament lamp has maximum emission at around 1 micron. Okay. So, which is what we would not like, because tungsten filament lamp, it is used for purpose of lighting, ideally should have had its peak emission somewhere in the wavelength range from 0.4 to. So, peak emission is not between 0.4 and 0.7 micron. So, this means that a tungsten filament lamp is not a very efficient device for producing light. For example, a typical 100 watt lamp will produce only around 8 watts of light radiation, that is emission in the range 0.4 micron to 0.7 micron. So, its efficiency is around 8%. For 100 watt of electrical energy consumption, only 8 watts is coming out as light. Okay. So, that is why in the last 10 years you must have seen that most people who are energy conscious are switching over from tungsten lamps to light emitting diodes. This is occurring because the efficiency of these LEDs is much higher than that of tungsten filament lamps, and hence they are more efficient creation of energy. Tungsten filament lamp ideally is more suited for infrared heating, because it generates peak radiation around 1 micron in the infrared. So, if there are applications where infrared heating is desirable, then you can go for tungsten filament lamp. But for purpose of lighting, tungsten filament lamp is not a good choice, because only about 8% of the energy is consumed by the filament lamp actually comes out as light energy. So, this is a weakness which you cannot do much about with reference to tungsten filament lamp. But other devices like LED take a different approach to generate this light source, and it is not, LED is not governed by laws of equilibrium thermodynamics. So, tungsten filament lamp is of course an old invention, goes back to the days of Edison, but it is now not finding a lot of favor with people who want to improve energy efficiency, because the lamp by its very design cannot really increase efficiency substantially. So, this must be kept in mind. Now, a little later we will tell you why you should realize by now that if the fraction of radiation lying between 0.4 micron to 0.6 micron is around 8%, that calls for some rethinking about how to utilize the filament lamp, because 92% of the radiation emitted filament lamp comes out as heat, and all of us are absorbing that heat. The room also absorbs that heat. So, in a hot climate, having tungsten lamp actually will add to your air conditioning load, because you are putting out more and more heat, and that heat has to ultimately will ultimately heat up the room unless there are ways to remove the air from so the tungsten filament lamp can never achieve high efficiency, because the fact is that it cannot go above 8%, because the temperature of the filament lamp cannot exceed 3000 Kelvin. So, that is the basic limitation of this lamp. It cannot exceed 3000 Kelvin, because the melting point of tungsten is close to 3400 Kelvin, and as you approach the melting point of the material, the evaporation rates go up dramatically. Now, I will give a little example of the empirical data we have for sublimation, that is conversion of tungsten to vapor, and so this is a value which can be shown to be around 10 to the power minus 6 into T by 3000 to the power of 30 grams per centimeter squared per second. Okay. This is this rate at which tungsten sublimates from the wire, and the key issue here is not the numerical value, but this power. So, notice that the sublimation increases almost exponentially with temperature, and it is going up at the rate of T to the power 30. So, even a few degrees rise in temperature will have a huge impact on the life of the tungsten filament lamp. As most of you realize, the tungsten filament is already very thin, and as the sublimation occurs and parts of the material become vapor, there will come a point where there will be one point in the filament where the amount of material is so small that it will break. And all of you who have used tungsten filament lamp would have experienced the fact that as the lamp gets older and you switch on the light and the voltage is somewhat higher than normal, then you will see the filament breaking. And so, because of high voltage, the temperature of the filament tentatively goes up by 10 to 20 degrees, and that is enough to bring about a catastrophic failure. So, that is why people designing tungsten filament lamp cannot afford to increase temperature beyond 3000. Now, if the temperature of tungsten filament lamp is kept below 3000, then you can see that it can have only 8% of the radiation in the visible. So, the upper limit of the efficiency of the tungsten filament lamp is controlled by the highest temperature that can be achieved there, keeping in mind that you need a lamp to have at least a life of 1000 hours, right. So, if you typically keep your lights on at night for 2 to 3 hours a day, you expect it to last about a year. So, the design of the tungsten filament lamp has to account for the fact that you want a minimum life of 1000 hours, and if that is the case, you have to keep a temperature somewhat below 3000 Kelvin, and because of that your conversion of the electrical energy to light energy is only 8%. So, when you put tungsten filament lamp in your room, 92% of the electrical energy that is consumed by the lamp is coming out as heat. So, in a country like India, tungsten filament lamp is heating a room more than lighting, and that is why most people are now switching over to light emitting diodes, although they are more expensive, but their efficiency being higher, in the long term they will achieve better efficiency or higher efficiency, lower consumption of electric energy. Now, let me take a few examples to illustrate how one computes total absorptivity and emissivity for materials. Now, let us take a typical example here of any material, and let us say the variation of directional spectral wavelength is like this. Now, in today's world, we will replace that by a series of values, step sign. So, let us say this is ith and this is I plus 1. So, the directional total absorptivity will be nothing but sum over all I, that is different regions here, from 1 to n, and this value let us call it as alpha lambda I, that will be alpha lambda I, that is the absorptivity of the material between lambda I and lambda I plus 1. Then you have to know the fraction of radiation lying between lambda I to lambda I plus 1. So, you have to know how much of the incoming radiation is lying between these two wavelengths. Then once you know that, you can compute this. Now, the information about the fraction of radiation lying between lambda I and lambda I plus 1 can either be provided directly to you based on some measurement, or if you know that the incoming radiation is proportional to a black body radiation at a certain temperature, then you can compute this from standard tables available in most heat transfer textbooks. The fraction of radiation lying between two wavelengths for a given temperature for a black body. For the same material, we know that alpha prime lambda is equal to epsilon prime by Kirchhoff law. The same material, you can calculate the emissivity, total emissivity, again as sum over I equals 1 to n. Now, alpha prime lambda and epsilon lambda are same, so I can use alpha prime lambda I. Now, we will use fraction of black body radiation, that is the weighting function for emissivity, between lambda I Ts to lambda I plus 1 Ts. This is available from tables in all textbooks. So, the main difference between the calculated absorptivity and emissivity is the value f you use. The value f for absorptivity is based on the how the incoming radiation varies with wavelength, while in the case of emissivity, we go by the temperature of the surface and we look at the black body function and compute the fraction of radiation lying between lambda I to lambda I plus 1 from the black body function formula. Now, to make all this very clear, I will take a very simple example to illustrate this. Imagine a material whose emissivity varies with wavelength in a very simple way. Okay. Below 1 micron, let us assume it has one value, and between 1 and 10 it has another value, and beyond 10 it has a third value. The numbers are assumed for this example is 0.9, 0.5 and 0.2. Okay. If the variation is more complicated, you can use more number of intervals. So, let us assume that this material is subject to solar irradiation, and solar irradiation can be assumed to be black body at a temperature of 5800 Kelvin. Okay. So, we know from the black body function that from f equals 0 to 2898 micron Kelvin, the radiation amount fraction is 0.25, while you go from f 0 to 5800 micron Kelvin, it is around 0.72. This is available from tables at the back of most books on heat transfer. Given those two information, you can estimate alpha prime as fraction of radiation lying between 0 to 1 micron, that will be 0 to 5800 micron Kelvin, that is 0.72. So, 0.9 into 0.72 plus the remaining radiation for sun lies between 1 and 10 micron, that is remaining 0.28. So, 0.5 into 0.28, there is no radiation beyond 10 micron for sun. So, these two will lead to a value of 0.788 for absorptivity. For the same material, if you look at directional total emissivity, you have to use and assuming surface temperature of the material is 289.8 degrees Kelvin, assumed for convenience, close to room temperature, and for this value at up to 1 micron there will be no radiation. Between 1 and 10 there will be about 0.25. So, we take 0.5 value from here, multiply by 0.25 plus the remaining 0.75 is here. So, 0.2 into 0.75, and this will give you a value of 0.275. Okay. And so, you can clearly see that for this material alpha prime epsilon prime is close to 3, not quite, but close to 3. So, this is somewhat selective like we saw in the case of metals, and so this was just to illustrate how you compute the total properties from spectral properties if you know piecewise values of these functions. This can be of course extended to any number of intervals, and this can be automated. You can write a computer program to calculate emissivity and absorptivity given the temperature of the surface and also the temperature of the incoming radiation if it is a black body. Now, let me give you another illustration. Now, as we saw, the directional emissivity of many materials values like cos theta. Let us assume it is 1 into cos theta, that is at theta equals 0, epsilon prime is 1, and at theta equals 90, epsilon prime is 0. Okay. Very simple variation. So, what will be the hemispherical total emissivity? This we saw from earlier lectures is nothing but E prime cos theta d omega. Now, this can be written as 0 to 2 pi for the phi variation and 0 to pi by 2. E prime is cos theta, there is another cos theta, you get cos squared theta, and the from the definition of d omega you get sin theta d theta d phi. Okay. So, this integrates to 2 pi. So, this becomes 2 times 0 to pi by 2 cos squared theta sin theta d theta, and if you assume sin theta is x, sorry, you can assume a much simpler one, you assume cos theta is x, cos theta is x, then dx nothing but minus sin theta d theta. So, this will come out, and when you go from x equals theta equals 0, x equals 1, but because of minus sign this will become 0 to 1 x square dx, which will integrate to 2 into x cube by 3. So, we will get an answer of 2/3. So, what you find is that the directional emissivity varies as cos theta. The hemispherical emissivity is 2/3 of the value of the emissivity, normal emissivity. So, directional emissivity at theta equals 0 is 1. The hemispherical emissivity now comes out as 2/3. So, you can see typically in many materials the hemispherical emissivity is about 2/3 of the directional normal emissivity. So, this is a useful information to have, because you can measure the directional normal emissivity fairly easily, because for an opaque material the sum of directional normal emissivity and the directional normal reflectivity is equal to 1. So, if you measure the reflectivity, you get the emissivity, and once you know that, if the material has behavior similar to what is given here as cos theta, then your hemispherical value will be 2/3 of the normal value. So, this kind of information is useful for many applications, wherein you have to estimate the hemispherical value from the directional value. Now, one more example I will give you just to make a point. We saw that for many materials emissivity is constant, equal to, let us say 1 for theta between 0 and 60 degrees. We saw that example in the figures I gave earlier, and after that it goes rapidly to 0. So, let us assume that goes to 0 for theta greater than 60. So, if you have this kind of behavior, then your epsilon will come out as 1 by pi, again integral over omega epsilon pi cos theta d omega, and once you do the integration, you get 2 into 0 to 60 degrees, because that is up to which emissivity is there. You will get sin theta d theta, because the values, there is no emissivity constant comes out, cos theta sin theta theta, and so you merely integrate this now, and when you integrate this now as before, you get a value of 3/4. So, in this case, where the material had emissivity variation which was a constant from 0 to 60 and went to 0 after that, for such materials you can see that the hemispherical value is 3/4 of the directional normal value, and this is somewhat higher than one we saw in the previous example where it was 2/3. So, that gives you roughly the typical expectation that the hemispherical value emissivity is somewhere between 2/3 to 3/4 of the normal emissivity. So, this information is useful for application wherein you may not get the hemispherical value and you have to make do with the value of normal emissivity measured in the laboratory, and from there you want to infer the value of the hemispherical emissivity. So, what we have done so far is we have highlighted the fact that for most real materials, both emissivity and absorptivity vary strongly with wavelength and somewhat with angle. And we have shown you how Kirchhoff's law can be applied for these materials carefully, not casually, as is done in some books. And we also showed how the spectral variation emissivity of many materials like metals and ceramic surfaces can be very useful in the design of tanks to keep the tank cool, or in designing solar collectors to increase the absorptive solar radiation, at the same time keeping the emissivity low. So, a good knowledge of the directional and spectral variation emissivity is very useful in the design of many engineering systems, and the challenge for the designer very often is to get the right data about these materials. We saw that for metals, the radiative properties is very sensitive to the oxide layer thickness. The oxide layer is there, the emissivity is much larger. Well, oxide layer is not there, emissivity is quite low. So, before we can assume a value emissivity for metals, we must be quite sure about the amount of oxide that is there in that metal. And an oxide layer is inevitable because many metals are easily oxidized, and you should expect it to have a certain amount of oxide layer unless it is freshly cut material. So, with this we complete our discussion on the radiated porous surfaces, and so we will be moving on now to next understand how we estimate the fraction of radiation that is there in one region, how much reaches another region. So, that will be the topic of the next lecture. Thank you.